And we are live and we are back to school. Thank you, everybody, for joining us today. This is going to be a really good technical seminar on everything you have ever wanted to know about performance with your Dash applications. Issues that you might run into running locally or that you might run into only in the perilous path to production. Thank you, everybody, so much for joining us today. If you have questions during the webinar, if you got questions right now, drop them in the chat. I will answer them all at the very end of the session, and we've got a couple support staff helping us out, facilitating this seminar today, and they can answer a lot of questions that you might have during the presentation. Also, if you have any performance tips that you would love to share with everybody else, things that maybe I didn't cover or didn't emphasize enough during this presentation, drop them in here. And during the end of the presentation, I will look through all of your questions and answers and share some performance tips from the community. So we'd love for this to be an active seminar as much as possible. Hey, that's me. I'm Chris Parmer. I'm a co-founder of Plotly, and in 2017, I authored the Dash library, which is what we're going to be talking about today. I had the product team at Plotly. We develop both Dash open source and Dash enterprise platform for all of our customers. We've come a long way over the last 10 years. Our libraries are downloaded over 15 million times a month. We've developed one of the most comprehensive visualization libraries out there, covering all types of charts, from scientific charts to business to 3D tables. Dash itself has a really rich set of components and an open component architecture where we have hundreds or thousands of components made by the community. Our customers and our community loves Dash because you can create applications that might otherwise take months or years to create. You can create them and bring them into production in days to hours. So really excited to share with you everything that I've learned about performance with Dash and give you an overview of how to make your Dash applications faster on the road to production. This webinar will be helpful for both folks that are using Dash open source and helpful to all of our customers that have joined us using the Dash enterprise platform. Big thank you to all the customers that could make it here today. So for those of you who are unfamiliar with Dash, just want to give you a quick update on how we think about Dash and how we explain it to new folks. So Dash applications are web applications. They are written in Python, and they are really well suited for data science and really anyone working with data in Python. What's exciting about Dash applications is the data analysis routines that you write in Python can then be accessible to other folks within your organization. They can access and run these computations and analytics through your web browser using a really nice graphical user interface full of controls and buttons and sliders and tables and charts. Dash apps are really unique and very different from the status quo of business intelligence or BI tools in that these Dash applications can run analytics on the fly. So you're not just limited to pulling in data that has already been computed or already been analyzed and displaying that. Your Dash applications can compute data, they can run models, they can do predictive analysis, historical analysis, all on the fly in Python as the users are interacting with the Dash application. Because these applications are written in Python, you've got all of the tools available to you in Python to create these applications, to run analytics, to analyze your data. And Python is sort of the Swiss Army knife of programming. It's got dozens and dozens of hundreds of different tools for analyzing different types of data and loading it into memory. So it can work really well with structured data. It can work with unstructured data, network charts, images, videos. You have a lot of control because you're building these applications in Python. Dash applications give you full control over the look and feel of the application. At the end of the day, it's HTML and CSS under the hood. So if you need to escape to control every aspect of the application, you can do so using the full power of all of the web technologies that are available to you. And a lot of our customers really like that. They get a lot of demands from their end users in the business, and that require a deep level of customization inside the user interface. Dash applications are built by the domain experts within the organization. And not everybody building a Dash application is necessarily a professional software engineer. Our customers are using Python just to get the job done, and they are professional mechanical engineers or biologists or computational bioinformaticians or statisticians. And Python is the tool of choice for analytics, and Dash gives you the ability to bring those analytics to life through a really rich interactive web application. So I think the first piece when we think about improving the performance of a Dash application is really understanding the architecture of a Dash app. And if you understand the architecture of a Dash app, then you can know where to look for performance issues and what different areas you can improve within your application. The key to making an application or any software fast is to know where it is slow. Where is the bottleneck? And then improving it from there. And to understand where the bottleneck is, you have to understand the architecture of the software that you're developing. So this is going to be a 10,000-foot view overview of what makes a Dash application. When you visit a Dash application, you're visiting it in the web browser, and that's all this box over here on the right. And the web browser is rendering your components. You open up a Dash application, it's going to load some data from the Python server, and it's going to convert that data into elements that you see on the screen. And there's a dozen of different technologies that are actually used to render those components on the screen. And all of those different technologies have their own inherent performance limitations. So if you're rendering, say, a simple table, that might be using HTML tables, and it might be using some CSS under the hood to display that table. And the browser itself has sort of an inherent limitation in the number of elements that it can view on a browser window. And we will see that as we dig into the performance. So just understanding that the browser is where the rendering is happening. The rendering isn't always happening, say, on the Python server. The Python server is sending data to the browser through callback output or through the app.layout, and then the browser is rendering that data into the components that you see on the screen. Your browser can also be running computations. It isn't just rendering data. It might be running computations to aggregate data, like in Plotly.js charts, if you're transforming a set of raw data into bins for displaying a histogram. In some cases, that entire raw data set is sent to the browser. The Plotly.js library that is running JavaScript code within the browser will crunch some numbers, and it will compute the different bins for those histogram bars and then display those bars. If you've written client-side callbacks in Dash, then those client-side callbacks are executed in the browser using JavaScript. And then finally, just transforming the data back and forth, receiving it from the network and loading it into memory itself is some work that the browser will do. The browser communicates to the Dash application server, and the interface for this communication in Python are the Dash callbacks. And the Dash inputs and states is pulling in data from the browser, and the Dash callback outputs are sending data back to the browser. So when you click a button within a Dash application, that button is going to have an input, which is going to be the n-clicks property of that button, which is going to represent the number of times that that button has been clicked. So the browser is going to send that data, n-clicks, which might be 0 or 1 or 2 or 3, and it's going to send that down to your Python code. Your callback will run, and it'll take that input argument as the function argument in the code that you write. Your Python code is going to run. It's going to take that number. It might take some other data from the UI, like the value of the dropdown or a slider. And with those parameters, it will crunch some numbers. It might make a query to a database. And the output of that function is going to get passed back up to the browser. And that output is going to either be an entire component itself or the representation of a component, which is going to be a data structure that will get passed to the browser, and then the browser will render that data structure as a component. The Python code is also going to be loading data in from a data store. That might be loading that data from a CSV or an Excel spreadsheet, and that might be loading it when the application starts, when it boots up. It might be loading that data on the fly within a callback. And that data store could be right next to the Python code. It could be in a CSV or an Excel spreadsheet that lives alongside the Python code, or it could be in a database or a data warehouse that is within the same server, running on the same server as a Dash application, or within the same region as or data center as a Dash application, or it could be running halfway around the world. And the Dash application could also be hitting an API, and that API could be, again, living on the same server within the same region or halfway around the world. So when we think about performance, we want to think about each of these individual sort of places where code is getting executed, whether that's running JavaScript code within the browser, whether that's running Python code within your Dash application, or whether that is executing a query within your database, data warehouse, API. And we can kind of think about those three places, but equally important is thinking about the data transfer in between these three places. The data that is passing over the network between the browser and the Python web server. That's passing over the network or over the file system from your Python code to the underlying data store. And the network can play a big factor in our performance. Our code might run really fast, but if it's transferring a lot of data over a long distance, then that can end up being the bottleneck. Now, networks are faster and faster these days, and what was a network bottleneck 5 years ago or 10 years ago might not be an issue today because of how fast the networks have become. And this will really depend on your own use case and where your own users are, where your data is stored, where your Dash application is hosted, whether your users are accessing your application over cellular, over 5G or 4G or 3G, or whether everybody accessing your application is going to be within a company VPN and very close to the servers. The other thing to think about with these three buckets is the sort of concurrency or the number of sort of copies of code or instances that are being run within a Dash application. When we work on our Dash applications in development, we're often just running a single process running our Dash application. We just type in our terminal Python app.py, and that's going to be running a single Python process serving our Dash application. And when we visit our Dash application in the browser, we're just a single user in a single browser. But Dash was designed to scale up to many concurrent users visiting your Dash application at the same time. And the way that you handle all of those concurrent users is you can scale up the number of copies or kind of workers or CPUs. There's a lot of different ways to kind of describe this that are running your Dash application in the background. So if you have 10 people visiting your Dash application at the exact same time, and those 10 people each click a button, and that button is going to fire a callback, and that callback is going to take, say, 5 seconds. There's no getting around needing to run that computation for each one of those users if it's all happening at the same time. So 10 users click a button, that button takes 5 seconds to run. If you're running just a single Python process running your Dash application, then it can only handle one request at a time. It's going to handle the first person's callback when they click that button. 5 seconds later, after the computation is finished, it'll handle the next person's callback, and then the next person's, and there's going to be some queuing set up in the system. The way to scale this is that you can run multiple copies of your Dash application, which can handle multiple concurrent requests at the same time. Dash is a stateless architecture, which means that one of these copies or workers that are running your Dash application can handle a request from any of the users visiting your application. So if you have 10 users visiting your Dash application, you don't necessarily need 10 workers to serve each one of those users. Each person doesn't need their own dedicated CPU or process. And in fact, you can usually have maybe 10 to 100 times the number of users as the number of processes that are serving your Dash application. So you might have 4 workers serving your Dash application, and that could handle, maybe 100 or 1,000 different users. And when we think about handling different users, there's that extreme case where all 1,000 of those people are visiting the Dash application at the exact same moment, and they're clicking that button at the exact same time. But in reality, you might have a lot of users, but they're not clicking that button at the same time. And if that user is just visiting your Dash application in their idle, they're just reading the application, they're looking at the charts, they might even be hovering over the points in the charts. There's some interaction within the Dash application that doesn't make any server requests. And so in practice, we can have hundreds of users or thousands of users visiting our Dash application and only a handful of processes that are serving the Dash application, because there is this sort of idle time in between the user interactions. So this is usually kind of this scaling model that we're thinking about. You'll want to run a few different copies of your Dash application so that the application is fast for any user visiting the application at a single moment, and so that any parallelization that can happen across those different processes. But you don't need sort of an absurd number of CPUs to handle a large amount of website traffic. So this model of thinking about the different sort of copies that are running of your Dash application, or thinking about many users visiting your application at once, is a really helpful model to start thinking about when you're developing your application, because it can affect the way that you architect it and the way that you think about scaling your application. Dash was designed to scale like this. You can very simply run multiple copies of your Dash application without changing much of your code. So if we think about, what is it that can be slow throughout the Dash architecture? And this kind of applies to almost any website out there. A lot of this stuff isn't necessarily unique to Dash itself, but is more sort of standard web architecture, full stack web architecture. The first thing is in the browser. You load up your Dash application. The browser has its own inherent limitations in the number of elements that can be rendered at the same time within the browser. And that's around 10, it's on the orders of tens of thousands of SVG or HTML elements. If you are rendering a Dash component, that component itself is going to be composed of, it's going to render down into HTML within the browser. If you're using Dash HTML components, then a single HTML component that you define within your Python code maps one-to-one to the HTML element that will be defined in your browser. But if you're using a higher level component, say like the data table, then in your Dash code, that's just a single component. But when that gets rendered in the browser, that's going to end up getting rendered as an HTML component with thousands or hundreds or thousands of HTML elements. And the limitation within the browser is not necessarily in the number of Dash components that is rendered, but within the number of HTML elements that are being rendered within the page. So your Dash app, you might think you're fine because your Dash application only has a couple of components within your layout, but the way that gets rendered at the end of the day in the browser might be rendering tens of thousands of elements. And the way you'll see this getting slow is the UI will just start to feel laggy. If you're rendering a huge table with 10,000 or 100,000 rows and you're scrolling through and it starts to feel a little bit slow, or you'll see that sort of infamous warning within your browser that says this page is using a lot of memory or it's using a lot of energy. Do you want to try refreshing? When you start running into those kinds of messages, it's usually because of the amount of elements that are being rendered on the page. There's different technologies that are being used within a Dash application or any website in rendering content. Most of the elements are rendering HTML and applying CSS to those HTML elements. Plotly graphs themselves, most of them by default use SVG, which is a vector graphics, and those face the sort of same limitations as HTML elements. Plotly has a high performance chart types that are enabled with WebGL, and those chart types can display orders of magnitude more data within the browser. They can display millions of data points. And you'll have the option in many chart types to sort of just turn on the WebGL mode. Scatter plots in particular, line charts have WebGL modes that can improve the performance. All of the 3D charts, because they're composed of many different points, also have a WebGL option. And then let's think about the browser to the Python Dash app network transfer. This is happening over the callback inputs and outputs. The data that's getting passed into your function as function arguments is coming from the web browser. So it's transferring over the network from the browser to your Dash code. And whatever you return from your callbacks is getting sent back up to the browser. And this network is really going to depend on your own, this delay, the performance here is going to depend a lot on your network, how close you are to your Dash application web server, and how fast your network is. When we're running our applications locally, and we open up our Dash application in that localhost 8050 URL in our browser, our user, when we're visiting that application in our web browser that's running on the same machine as our Python code, that network is really fast because it's not going anywhere beyond our own computer. So when we work in development, this particular network delay can be really deceiving because when we deploy our Dash application, that deployment will go to a server that is not on the same computer that we are developing on. And there will be an inherent network delay that will be introduced in deployment that we might not see when we're working locally. So the types of limitations that we deal with here really depend on your network. And I guess as a rule of thumb, you can think about passing around between 1 and 50 megabytes of data back and forth between the browser and your Python server before you'll start seeing delays. And then the next piece is what's happening within your callback itself. You are often going to be computing data, and there's hundreds of different ways that you can make computing data faster. Some of the stuff is just going to be within your own numerical methods that you're writing. Other things will be the types of libraries that you are using and the optimization techniques that are available within those libraries. Because these Dash applications can be handling many users at once, or even for just a single user, multiple callbacks can be executed at once. There can be delays within your Python Dash code just around waiting for a worker to be available to run a callback. If you have a Dash application that is running a single worker on a single CPU, but your code is structured in a way that multiple callbacks can be run at once, because your application is running just with a single CPU or worker, it's only going to be able to execute that callback one at a time. And so you can get a lot of performance boost just by boosting the number of workers that are available. Sometimes our Dash application code isn't actually computing any data itself, but it's just waiting for that data to come back from the web server or from the data store. And that brings us to the next point, optimizing the queries within our data store and the data transfer from our data store to the Dash application. And this data, this could be on a file system or CSV. And in that case, the sort of network transfer is more, it's not really over the network, but it comes down to the speed in which files can be read off of disk and transformed into memory. In other cases, our databases will be in another data center or another server, and then the network delays might be much larger than the time it takes to actually query that data. In some cases, we're going to be querying and aggregating all of our data in Python, say in Pandas. So we'll load a huge data set from the data store into memory, and we'll crunch the numbers in Python. In other times, we'll push those queries back to the data store. and we'll have the data store itself run those aggregations and filters. And when to sort of do these aggregations in memory in Pandas versus in data store will depend on a lot of factors. There's not one clear silver bullet answer here. In some cases, you're going to be computing data on the fly and you need that data in memory in Python. The data store that you're using or the database or data warehouse might not have the level of expression available to it in order to be able to compute the data that you need to compute. In other cases, running the data in memory and aggregating it in memory in Pandas is going to be faster, but you'll get to maybe a certain point where it's no longer feasible. So if we think about, this is kind of the architecture, these are the different places that the application can be slow. How can we make it faster? And we really have to look at each one of these steps and think about the different ways that we can make this application faster. And there's different solutions for each one of these steps. This is sort of a cheat sheet that I've made to talk about the different solutions at each stage of your Dash application architecture, from the browser to the network to the Python server to the network delay between the Python server and the database. And I just want to walk through a few of these. So within the browser itself, if we're limited by displaying 10,000 HTML elements, then the easiest thing we can do is just display less elements. We can do this in a variety of ways that are actually really user-friendly and actually might give our users a better experience overall. Does the user really want to see 10 million data points in a table? Will they really scroll through all 10 million rows or not? Or can you instead pre-compute some aggregations or some summary statistics and display that to the user? Or could you display some filtering and some controls to allow the user to filter out the data that they want to see instead of scrolling through 10 million rows? And the filtered data might only be 10 rows of data or 100 rows of data, and you won't be seeing the same performance limitations. There's other solutions here like pagination or filtering the data on the server. So instead of sending all 10 million data points over a network, you might just be displaying 100 at a time, and you might have a button that says display the next 100 rows of data. Dash was designed in a way that components could either render all of this data within the browser client itself or render data sort of progressively. So a data table, for example, you could paginate page data 100 rows at a time and only display and transfer those 100 data points over the network at a time. Same thing with cytoscape network graphs, for example. You might display just a single point in your network, and as you click on that point, you'll fetch more data from the browser and progressively display your network chart. So instead of displaying 100 million network points in your cytoscape graph, you're displaying 10 at a time. And as the user interacts with your application, they're progressively seeing more data. This applies to many different charts and many different components within Dash applications. On graphs, you can hover over points and progressively display more points within a separate chart. Tables, you have pagination, cytoscape network charts. Even in third-party components like Leaflet.js, you can display data progressively in this way. If you're displaying a bar chart itself, do you need to display all million points within that bar chart, or can you perform some summary statistics and display a grouped bar chart with some aggregations being done? If you're displaying, say, a time series chart, do you need to display all of the raw data, or can you compute a window so you're displaying, say, a 10-minute rolling average, a 10-minute rolling maximum, and a 10-minute rolling minimum, and you have sort of bounded in between the minimum, maximum, and the average, and you're displaying 1 point every 10 minutes instead of a million points if they're sampled at a really high frequency. So there's a lot of things that you can play with within the user experience to sort of just display less data, which will end up providing a faster experience for your user because you're displaying less data and you're transferring less data over the network. Within your Dash application itself, A quick win is just increasing the number of workers that are running within your Dash application. Dash callbacks can be run in parallel if they don't depend on each other. So if there isn't a callback chain and these callbacks are written next to each other and they aren't dependent on each other, then when a user visits the application, the browser is going to make separate network requests for each callback that can be run. And so if you just increase the number of workers that are servicing your Dash application, then more of these requests can run in parallel. There's other tricks that you can do within structuring your Dash callbacks, where instead of having multiple callbacks that are separate, that each need to be run independently, you might combine them to have a single callback that has a multi-output so that multiple components can get updated on the page from a single request. The next piece is just making your code faster itself. This is sort of outside of Dash itself and is more within your own Python code that you are running. And there's so many different great tools available in the Python data ecosystem to help you out here. If you are using lists today, you might consider using NumPy arrays, which allow for vectorized operations that can be much faster. If you're writing a lot of numerical methods yourself within NumPy, you might try out the numba decorator, which can provide some speed up for some numerical methods that you'd write in NumPy. If you are working in Pandas and you're running into a limit in the amount of data that can be processed within Pandas, maybe around, say, 5 million, 10 million points, you might consider using an alternative data frame library like Vaex, which will work out of memory, but has great parallelization that happens sort of for free under the hood and can scale to tens of millions or hundreds of millions of points without needing to resort to a different data warehouse. You can cache your data so that instead of when the numerical method is run once, the result of that method is stored, and the next time it is run, it is fetched from memory instead of recomputing that data. That can make subsequent queries and subsequent hits to that function faster, but the first time that function is run, it's still going to be slow. So if that function takes a couple of minutes to run, you might need to hit that function as part of your application warm-up to sort of warm up the cache. Otherwise, the first user that visits your application will wait 2 minutes, and then every other user visiting your application might wait, half a second. And there's a lot of sort of other tricks within the Python ecosystem. Some things you'll end up getting for free. Python 3.11 is coming out in October, and for some numerical methods, people are reporting that it's about 20% faster, without needing to change any of your code. So just updating your version of Python and keeping track of the release notes in the Python version that you're using, as well as any other packages that you're depending on, you might get a lot of performance improvements sort of just for free. And then the next piece is on the data store. And this is going to be really dependent on your own use case and the technologies that you have available to you. For smaller amounts of data, it is generally going to be faster for you to load all of that data into memory and compute that data and process that data in memory. And in some cases, you can really increase the amount of memory that's available to you within your server, within your development environment, and get really far without needing to do anything more sophisticated. But at some point, you'll hit a limit in the amount of data that you can hold into memory, and that's when you might start looking into alternative tools that can process that data more efficiently. That might be data warehouses or databases. That might be tools like Vaex, which work with HDF5 files and sort of read the files incrementally and process the data in chunks, sort of streaming from the file system. Anything that is going to be out of memory is usually going to be 10 to 100 times slower, but it'll be able to handle a lot more data. And even though it might be slower than memory, it might just be fast enough. And this is going to really depend on your own data set, how many rows of data you have, how many columns of data that you have, and the data types that you're using and the types of computations that you need to do with your data. You might have no choice but to load this data in memory because of the computations that you're running. Or if you're just aggregating or filtering data, it might be easier for you to do all those aggregations and filters in the database. It might come out to the different preferences that you have. Maybe instead of writing Pandas code, you prefer writing SQL queries, or vice versa. And that might end up determining the technology that you'll use, because bringing your application, the time to market to bringing your application into production might be more important than the performance improvement that you'd get from the technology that you'd use. Start with something, measure it, think about the amount of data that you ultimately need to be able to view and process, and then go from there. There's different techniques that we can use just within the data pipelining of Dash applications, where if something takes too long to do on the fly within a callback, you can do it in advance when the application starts, or you can do it in a periodic background task in the background. So you might have a SQL query that can load all of your data into a Pandas data frame. Are you running that query on the fly within your callback, or are you running that when the application boots up? You might have an application initialization routine when your application boots up that could take 5 minutes, and that's totally okay because users aren't waiting those 5 minutes. Once the application is booted up, then when they visit the application, your callbacks will run, and those callbacks will run really fast because all of your data is in memory. And if that data is changing, if it's real time or if it's time based, then instead of loading that data when the application starts, when it boots up, you might be loading that data in the background in a background task periodically. So every day or every hour or every 5 minutes, it's querying that data from a data store. It's loading it into a cache that lives close to your Dash application, whether that's in Redis or in the file system. And then your application is reading from that cache. So you have this sort of background task that is running, that's performing the slow query and loading it and caching it closer to your Dash application. So within your Dash application callback, you can fetch that data from the cache, and you don't need to be reaching out to the data store where running that query might be slow or the network might be slow. And instead, you can cache it a little bit closer. So that's a really powerful technique to think about improving your Dash application's performance just in where and when you are processing your data, and when and where you are loading it into memory and then sending it up to the browser. So now that we kind of know a set of different tools that are available to us, different techniques we can do to improve the Dash application performance and where it might be slow, the next piece is to actually measure it. And I cannot overemphasize how important this is. It is really easy to jump to conclusions and think you know where your application is slow. And I feel like no matter how experienced you are, it is still very easy to skip this step. And I often will still skip this step of measuring my code. I will think that I am smarter than the code and I just know where the performance bottleneck is, and I will over optimize in some place of the code where it actually does not really matter. And in some of these techniques that we talk about, it can actually make your code slower if you switch to the wrong technology prematurely. You might think, okay, Pandas is never going to be able to handle the volume of my data. I have to use a data warehouse. But maybe for the size of data that you're dealing with, maybe it's small enough where the overhead of using a data warehouse and transferring that data over the network and running that query somewhere else is actually much higher than just loading that data into memory with Pandas. And for each one of these things, there's those types of trade-offs. These trade-offs are often around the size of data that you're dealing with. Often, if the data is slower, it can be faster to do the thing where we load it all into memory. And that applies to the data processing that we do. That also applies to the types of components that we're rendering within the browser. You might think, oh, I need to paginate my data because Chris said that paginating is faster. I can't display too many HTML elements within the browser. But that's only once you get to, say, 10,000 elements. And before then, preloading all of that data into memory in your browser means that there's no more network requests that are happening as the user is interacting with the Dash application. It's all happening client side, and that can make your application feel really snappy. So you really need to measure your code. Write your application and then visit your application. It's best if you can deploy the application somewhere so you can see real network delays and start to look at where the performance bottlenecks are. There's a lot of different great tools to do this. Within Dash itself, you have this DevTools UI in the bottom right corner where you can look at each of your individual callbacks and see the compute time and the network delays for each of your callbacks. This gives you a really good high-level overview of where are things being slow within the network, just transferring the data, where is things being slow within the callbacks themselves, are things getting parallelized or not? When you look at this structure, if there's a lot of sort of parallel structure, then increasing the number of workers allows these things to run in parallel. This is a really great place to start. The next place I would start is by running this profiler middleware. And you can just add this snippet to your Dash application. And when you add it, you'll get this printout in your terminal that is showing all of the different places within your code and how long it is taking for each place in your code. And so you'll see the amount of cumulative time that is being sent in the functions. You'll see the number of times those functions are being called. In some cases, you'll see crazy things where some low-level function like converting a number to a string is being called 1,000,000 times. And even though that takes a very, very little time each time you call it, because it's being called 1,000,000 times, it starts to add up. I like to sort by cumulative time when I look at this data so I can see at a very high level where in my code things are slowing down. You'll need to look through these files and you'll see code that is within third-party packages that you're using and the code that is being used within that you've written yourself. And it takes a little bit to kind of read, you have to be kind of careful to read through things line by line and get an understanding of where things are slow, whether it's in your code or whether it's in some third-party package. This tool also comes with, is compatible with this other visualization tool called SnakeViz that allows you to visualize those results in this nice graphical interface here, which can be a little bit easier to parse sometimes than looking through this text output in the terminal. And what you'll see when you analyze this is you'll see these high-level functions. It's a call stack. So you're seeing the first function that's being called, and that function is going to call maybe a couple of other functions that'll call a couple of other functions, and they all sort of add up to the top. So it takes a moment for you to kind of look through here and parse down and see, oh, okay, now maybe subplots.py, that's a function that or a file that is within my code base that I wrote, and I can see where this is actually getting might be slow. And if you don't recognize these file names, then it might be within a third-party package that you may or may not have control over in order to improve the performance. The final tool that I'll use is the browser's network tab. And this will show you in a little bit more low-level detail the types of network delays that you'll see within your Dash application. You'll see how long things are taking to go over the wire. You'll see the amount of data that is being passed over the wire. And you'll see the order in which things are getting run. If you're looking within your network console, when you click on elements within your Dash application, you're clicking on buttons or sliders, you'll see this network request come up that's called Dash update component. And that is the HTTP request that is firing your callback. And so when you see that, that is sort of the request to look at. You'll see a lot of other requests come up that's around serving the JavaScript or HTML. Reload hash is handling the hot reloading during development that won't apply in production. So look for that Dash update component network tab. So we're just running out of time now. I want to give some folks some time to ask any questions that they have and for me to answer some questions. I've got a lot of code snippets. We've written a lot of code snippets that accompany that cheat sheet that I showed you, and we're going to be publishing those code snippets to GitHub so you can work through some of these different solutions on your own and kind of get a sense of, okay, loading this data, into memory is indeed faster or slower than loading this data from a database at this size volume, but not at this size volume. Again, the important thing is for you to run this on your own, measure it, and find exactly where the code is slow, whether it's in the network or in the computation, and then work from there. Working through some of these examples that we'll publish can help you gain an understanding of the different architectures that are available to you to improve your code. So I'll just take a moment here and look through some of the questions. Okay, we got a really great question from a couple of our Dash Enterprise customers that are on the line. Many thanks for joining and for your support. And they were asking about what types of performance tools or technologies should they be aware of when they're using the Dash Enterprise platform. And let me just open up the Dash Enterprise UI and talk through a couple of these. So one of the tools that I talked about is this ability to cache your data, and that's caching it. So maybe you are you run your computation one time, and then the next time that it is run, it is being cached so that and pulled from memory so that the computation doesn't need to be rerun. And a great caching service is Redis. This is free and open source technology. And you can kind of think of Redis as this in-memory data store that's available to all of the processes that are running your Dash application. You can't always just cache your data in Python because you might have multiple copies of your Python server that are being run. And so if you have multiple copies that are being run, then you want to read from a centralized in-memory data store so that one worker can cache something and then the next worker can read that cache. Otherwise, if they're each caching things individually within their own Python process, then you don't get that sort of shared expertise or that shared data caching from doing something centrally. So to use Redis, that's another service that needs to be available to you during development as well as when you deploy your application. In Dash Enterprise, we've made this available so you can add Redis or Postgres databases to your applications with one click. And these Redis and Postgres databases are available to your application. Redis and Postgres is also used not just for caching, but if you are running periodic tasks in the background that is fetching data from a data store and storing it somewhere for your Dash application to read. They're also used in running background callbacks, which can improve the scale of your Dash application. The other tool, if you're using Dash Enterprise, that I really recommend for doing performance work is the workspace environment. The workspace environment is a hosted IDE that is run on the Dash app platform. And the reason that I recommend this, especially for performance work, is that the workspace environment is very similar to the deployed application. So when I was talking about all these different ways that the application can be a little bit different in development versus production, if you're working in workspaces, a lot of those differences go away. So for example, the network speed itself. When I run an application within Workspace, it's running on this server, and that's going to be the same server or cluster that is running the Dash applications. So the network delay that I would see in loading the application in the browser and making that network request to the server, that network delay is going to be the same in development, working in a workspace, as it is going to be in production. So this is one way that you kind of won't get sort of surprised when you deploy your application into production. There's a lot of other similarities, like similar Python version operating system. You know, this is running in a Linux Docker container, and that's going to have different performance characteristics. Access to Redis and Postgres is available within workspaces. So this removes a lot of the sort of subtle, tricky differences between working in development, you know, maybe on a Windows laptop locally, and then deploying your application in production. And a lot of those differences can be really tricky to nail down, which is one of the reasons why we developed the workspace feature within the Dash Enterprise platform. And remember, there's that network delay not just between your user's browser and visiting the Dash application, but within the Dash application and visiting the data store itself. And so when you're working locally, that network delay might be different than when you're deployed your application. And Workspaces is just a really great tool for being able to better diagnose these issues during development rather than at the very end of your process once you've just deployed your application to production. So keep these questions coming in. Let me read through a couple of them. So one question was, what are the optimum resources which one can allocate for a Dash app on the cloud so that can handle thousands of rows of data daily and that is scalable? If we're just dealing with thousands of rows, then you won't need very much hardware at all. It is once we start getting into millions, or really tens of millions, hundreds of millions, or billions, where you need to start thinking about a lot of these performance characteristics. If you're just dealing with thousands, then in your Dash code itself, it can load data into memory in Pandas. They can be fetching that data on the fly from a data store, and it will be fast enough. Once you start getting into the millions or tens of millions or hundreds of millions, that's when you might need to think about, okay, am I going to increase the amount of memory that is available within the Dash applications, or am I going to use some other data store available, like a data warehouse, or use a tool like Vaex to load that data from disk, something that allows you to go beyond the inherent limitations of dealing with data in memory. Dash applications, though, they are written with a stateless architecture. They have all the Python tools available to you, so scaling them up to hundreds of millions of rows or billions of rows of data is no problem if you have the right tools available to you. And thinking about data that is updating daily, again, if it's just thousands of rows of data, then when you click on that button within your Dash application, it could fetch that data on the fly, no problem. But if fetching that data takes a little bit of, takes a long time, then you might think about querying that data in advance on a background schedule, loading that data into memory in a Redis database or onto a disk that is close to your Dash application, and then have your Dash application read that cache data that is closer to your Dash application rather than fetching it from the original data store on the fly. There is a question about security in Dash. So when my data is shown in the browser, is there any wall that protects the source data? That is a really great question. And the way to think about it is when you are writing your Dash application, anything that is described in your outputs that are returned from your functions is going to go up into the web browser. Any data that is outside of that, that is just in memory in Python, is not going to be available to your users. So you might load some data set in here that is going to be, some secret, say, maybe it's clinical trial data. We've got a lot of customers in the pharma space, so that's kind of top of mind for me. And maybe not everybody can access all of the data within this original data set. Now, just because you load this data into memory within the application itself does not mean that this data set is available to all the users in the Dash application. You have control over what data you are sending up to the web browser. So you might be filtering out this data within your Python code and then just displaying a subset to all users. If you're using Dash Enterprise, then you can actually get the username of the currently logged in user that is visiting your Dash application and use that username within your own business logic to filter out the data. Same thing with groups. So if you have a user that is part of a group within your own identity provider within your organization that is part of the clinical trial 1 versus clinical trial 2 group, then you could filter out that group and then use that group within your business logic in filtering out your data and display a subset of data to that particular user that is logged into your Dash application. And the sessions of Dash apps are totally independent. So what one user sees when they open up their Dash application is totally independent of what the next user sees. And this is part of the stateless nature of Dash applications, where the functions are going to just be returning data up to the browser. Each session is managed independently. All of the state is stored within the browser, unless you're using some kind of shared memory like Redis. So that's the way to think about it, and that's, this is sort of unlike, say, hosted Jupyter, where if you're sharing a hosted Jupyter notebook to your end users, they're going to see all of the data, have access to all of the data that is used within your routine. With Dash, you have a lot more control about what data you are sending to your end users. We're going to look through a couple of, we'll do one more question and then we'll wrap it up. There is a question about, kind of follow-up question about what I was just talking about, handling the username of the Dash applications. When you're running your Dash applications on Dash Enterprise, the platform handles this user authentication middleware. So as a Dash developer, you don't need to integrate any of the sort of identity provider integration with LDAP, OIDC, SAML, Okta, Auth0, Active Directory, all of those types of identity providers and protocols. The platform itself handles that for you. So when you set up Dash Enterprise, you will configure the platform to work with your identity provider, and then those features like passing the username down, sharing your application with just a subset of users, not all users, passing in the group, all of that is handled by the platform itself. And in general, I would recommend not trying to roll your own authentication or login code yourself, especially if your data is sensitive or secure. It is very easy to do it wrong or to miss something that is very subtle and that can be exploited. And so, this is one of the areas of value that Dash Enterprise provides, is this really well-tested, really robust user authentication handling to your Dash applications that you don't need to worry about once you license the platform and install it within your own organization, within your own data center. Then all of your applications get this login features and authentication for free, which, as we mentioned earlier, can fit into the performance story around that kind of row-level security use cases. Dash Enterprise runs within your own data center. We do not host Dash Enterprise for you. You install it, the platform, within your own data center on your own servers, whether that's on Azure or GCP or AWS or on a bare metal server within your organization. And when we think about performance, that's an important distinction, because where you are running your Dash applications can improve the performance. You want to run that Dash Enterprise platform close to, within your own data center, close to your underlying database, so that the network delay can be fast. So with that, I'm going to wrap it up. We will send you some of these resources from this webinar. Thank you so much for coming back to school today. This is a joy and a great pleasure to give this presentation, and I appreciate everybody taking an hour out of their time. Let us know if you have any feedback, and we'd love to do this again. So keep an eye out for future webinars by us, and good luck out there.